Okay, so now that we have relations, our next step is to build functions. Okay, so I mean, functions are definitely very important for mathematics, but all we have is sets, so we need to build the functions from sets. So let's start asking what is a function. So for example, the square is a function. You input a number and it gives you back the number square. Okay, so x squared is a function. Hair color is a function. You input a person and it gives you a color. So for mathematicians, a function is not just something that takes a number and you apply square roots and squares and plus and times. There are many kinds of functions. A function is just something that you input something and the function is going to give you back an output. So that's what a function is in general for mathematicians. But we want to model that with sets. So let's draw, for instance, here the square function. That's the function x squared. Okay, it's a function. How can we look at it as a set? Do you guys remember what the graph of a function is? So the graph of this function is what? Is a set like what I just draw right here. This picture I just draw is a subset. This is r squared, and what I draw is the graph, right? And the graph, what is the graph? The graph is the set of all pairs x comma y in r squared such that y is equal to x squared, right? So that's the graph of the function square. And if you have the graph, essentially you have a function. And look, the graph is a set. It's not only a set, it's a set of pairs, right? So a set of pairs, we already know what set of pairs are. We call them relations. So the graph of a function is nothing more than a relation. But not every relation is a function, right? Because if you have a set that looks like that, it doesn't look like the graph of a function, no? No. So what makes a relation a function? Okay, let's write it down. So definition. A function is a relation such that what does the relation need to satisfy to be a function? What's wrong with this relation right here that doesn't look like the graph of a function? What's wrong with this one is that if we take an element here, let's say x, and we want to know what's the value of x, well, there are this value, there are a bunch of points here. Which one is the value of f of x, right? So that's the problem with that one. That one, there is no unique possible value for f of x. While in this one, if you put x is equal to x, we know this one is the value of f of x, right? So how do we say that? So a function is a relation, let's call it a function f. It's a relation such that satisfies that every point gets mapped to at most one point. So that for every x that belongs to the domain of the function, and the domain of the relation is the same as the domain of the function. So we know we defined domain already. So for every x that belongs to the domain of the function, there is a unique y such that x comma y belongs to the graph, right? So for every point, there is a unique y such that x comma y belongs to the graph. So if you take a point here, there's only one value right there. Okay, so that's what makes a relation a function. Okay, and this is a funny way of writing x comma y belongs to f. So this unique y, so we call this unique y the value of f at x, and we denote it by f of x. Alright, so that it's a unique y, so we can put it the name because it's unique. We call it f of x, or the value of f at x. I mean, you knew this before, but now we are defining everything from scratch. Okay, so we can talk about functions using their graphs, which the graphs are set. Okay, what else? So we say that f is a function from a to b, or in other words, that f maps a to b or we just write f from A to B if what? If A is equal to the domain of A of f, which we defined in the previous video, and the range of f is included in B. Notice we don't, to say that the function goes from A to B, we don't require B to be exactly the range, just something that contains the range. The image of all the values of f are going to be inside. Right, so if you have f, if you have A right here, and B, and f goes from A to B, then every point in A has an image, but the range is going to be a subset of B. When the range is actually equal to B, we say that the function is onto. So if range of f equals B, we say that f is onto B. So notice being onto is a property of kind of both f and B, right? I mean, every function is onto its own range, right? But sometimes B is larger than its own range. And we say that f is 1 to 1 if you can never have two values that go to the same value. If whenever f of x equals f of z, we have it's because x equals z, right? So you can never have two different values going to the same thing. So only one value goes to one value. That's why it's called 1 to 1. Okay, so let's do a new definition. Given a set A and relations f and g, which actually we're going to think of them as functions, but this definition is going to work for relations in general. So let's assume only that we have relations. So first, A, the inverse of a function or of a relation, f to the minus 1 is defined to be what? So now we want the function to take the range to the domain backwards. So it's going to be the set of pairs y comma x such that f of x equals y, right? So, but this is not a, we're saying these are not functions. This might be, well, they might be functions or not. All we're assuming is that they are relations. So maybe we cannot do f of x because maybe it's not a function. What are we going to say here? Instead, we're going to say x comma y belongs to f. Okay, so the inverse is just flipping all the pairs in the relation. And the composition. So again, you guys know how to compose functions. That means you first apply, in this case, first apply g, and then you apply f, and then you get the composition of g and f. We can compose relations. We don't need to have them to be functions. And what are we going to get? We're going to get the set of all pairs x comma z such that x goes to something through g and that something goes to z through f, right? So we're going to have, this is the set of x comma y such that there exists x comma z, sorry, there exists a y such that x comma y belongs to f and y comma z belongs to g, right? So x goes to y goes to z. The restriction of f to a set A, here again this works for relation, and it's just we're going to restrict the domain to A. So we're going to forget about everybody who's not in A, at least in the domain. So it's a set of all x comma y that belong to f such that x belongs to A. So only we consider only the ones such that the first entry belongs to A. And the image of a set, that's the last one I want to define, of A under F is denoted F with this bold double bracket. is going to be the image of all the elements of A. So it's a set of all the y's such that there exists an x in A such that x comma y belongs to F. Alright, so all the y's that are related to somebody in A. Okay, let's look at an example. Suppose that F is a set of pairs 1, 2, 3, 1, 1, 3, 2, 2. I know we don't have numbers yet, but we're going to have them later. So let's just assume we have the numbers just for the example. 1, 3, 3, 2, 2, 1. Okay, and let's say that A is a set 1, 2. Okay, so first, is F a function or not? Well, no, it's not a function because 1 gets mapped to both 1 and 3. So in a function, every element must be mapped to at most one thing. Here it's mapped to two things, so it's not a function. So no function. What about G? G, 1 goes to 3, 3 goes to 2, 2 goes to 1. Every element goes to at most one element. So this one, yes, this one is a function. Okay, but it doesn't matter that F is not a function, we can still apply all these operations. So let's see what we get. Let's see what we get one at a time. So what is F inverse? Well, you have to just flip all the pairs, right? So we get 2, 1, 1, 3, 3, 1, and 2, 2. I just flip each pair one at a time. What about F composed with G? What do we get? Well, we have to start looking at the y's, such that if you start with G, you get to y, and then through F you get. What about F composed with G? So let's see. Okay, so we got to start with G. So let's start with the 1. Where 1 can go? Through G, it can only go to 3. And then 3 through F can only go to 1. So we get 1, 1. 2 through G, it can only go to 1. 1 through F, it can go to two things, 2 and 3. So that means we get 2, 2, and 2, 3. And 3 through G can only go to 2. And 2 through F can only go to 2 again. So we get 3, 2. And that's the composition of F and G. And again, it's not a function because 2 is going to two different things, 2 and 3. But it's okay. Composition of relations is only a relation. What about F restricted to A? So that means we only consider the part of A, we only consider the part of F where the first element belongs to A. A, we say, is the element A is 1 and 2. So where are these 1 and 2 going? So the second tuple, this one, is the one that is not, the first component is not in A. So the other ones are in A. So then we get 1, 2, 1, 3. It doesn't matter that the 3 is not in A. It's the one that it matters. And 2, 2. Okay, so that's the restriction of F to A. And what is the image of F under A? Well, we have to see where 1 goes. 1 goes in F to 2 and to 3. So we get 1. No, sorry. So we get 2 and 3. And 2 goes to 2 again. So we get 2 again. But we already have 2, so we don't need to put it again. That's the image of A. Okay, here is an observation for you guys. Let F be a function. Then what is F inverse composed with F? Suppose the function goes from A, from a set A to a set B. And here is your function F. here is your function f inverse. What is f composed with f inverse? Is going to be the identity in A. It's the identity function on A. What is the identity function of A? It's a set of all pairs x comma x such that x belongs to A. So every element of A is mapped to itself, right? We all know this. Okay, let's see some situations where we can get like partial inverses for functions. So let again f be a function from A to B, and let's assume that A is not empty just for triviality. So I want to claim two things. Number one, there exists a left inverse of function g such that g composed with f is the identity on A if and only if f is what? Let's finish the theorem and then let's see if we can figure it out. And B says that there is a right inverse such that f composed with g on the right is the identity on B if and only if f is what? Okay, let's start proving whatever with one direction and then we see what we need. Okay, so let's see the proof of this. It's hard to see a proof of something, we don't know what it is, but let's see how it works out. Let's consider part A, and let's consider the direction where our objective is to build such G, like this one, where our objective is to build a G like this one, and we want to know what do we need to assume about G to define such a C. So the idea is as follows, right? So we have a set A, and we have a set B, and we have our function f, and we would like to define G so that when you compose, we get the identity, right? So suppose we have an element here, B, and we want to define G. But what do we want? We want that if we have an element A up here, and we apply F, and we get to say f of A, then when we want the image back, we want to get that if you apply the image back, we get back to that one, right? So we would like A to be equal to G of A, G of B to be equal to A, right? So that's what we would like. So given B in B, if B belongs to the range of F, and B is equal to F of A, then we let G of B be that A, right? If we do that, then when we do A, apply F, and then apply G back, we get back to A. Okay, so what is the point here? Well, what if this B is also equal to F of A prime for some other A prime that goes also to B? Well, in that case, we don't know which to use for G of B, either A or A prime. So in that case, we get into trouble because we will get that A prime goes to B and then goes back to A, not back to itself. So we cannot let this happen, right? So the only way for this to work out is if f was 1 to 1. In this case, there's a unique such A that maps to B, right? So that's what we need. F is 1 to 1. If f is 1 to 1, then we can define this G. One other thing. What is if B is not in the range of F? Well, we let G of B to be any element of A. It doesn't matter what it is because it's not coming from anybody, so it doesn't affect G compose F. So we let A 0. And recall that A is different than the empty set. So we can take some element, let's say A0 belongs to A. Just fix an element that belongs to A. We know that it is one because it's not empty. And everybody that is not in range, we map it to it. So that's how we get this proof. What about this side? What now? Now this will make more sense. Suppose that we have a G such that G composed with F equals the identity in A, and suppose also that f of x equals f of y. We want to show that x hat is equal to y. Well, if f of x equals f of x equals f of y, if you apply g on both sides, these two should still be equal because we're applying g to the same thing. And g composed with f is nothing but identity, so this one should be x, and this one should be y. So we get x equals y. Alright, so we get that it has to be one-to-one. There was no other option but it to be one-to-one if you wanted to build such G. What about the other case? In the other case, what we need is G to be, you guys can guess it, onto. That's what we need. Why is that? Let's do the easy direction first. So if you take any B that belongs to B, we know that identity B is equal to the identity on B, which is equal by our assumption F apply to G of B. So that means B is in the image of F, right? So that means B belongs to the range of F because it's the image of G of B, right? So we get that everything in B is in the range of F. So F is onto. Now let's prove the other direction. Let's do a little picture. Here is A, here is B. We are given F. We want to define G so that if you're given B right here, we want G of B to be something that when you apply F back, you get back to V. So we want, so given B that belongs to B, we want G of B to be so that F of G of B equals B. So in other words, we want B to belong to the preimage of B. B is something that when you go back through B in F, you get there. So we are assuming that F is onto, so there's always something that goes to B, but there could be a bunch of things that go to B. We just have to choose one, right? So we will say for each B in B, let G of B be an element of F minus 1. Or in other words, we want let G be a function such that G is a subset of F inverse. G of B is an element of F inverse of B for every B. And domain of G, we want it to be B equals B. Alright, so if we do that, then we get our inverse. Question. can we find such G given the axioms that we have so far? So in the previous case, when we defined the inverse for the one-to-one, well, there was a unique element that was used for G of B. But here I'm saying for each B, just choose some element that belongs to this guy. Just choose one. I mean, we know there is one because it's onto. So for every B, just choose one element in there, and that's going to be your G of B. There is one, so we can choose. For each B, we choose one. For each B, we choose one. But that doesn't follow from the subset axiom, right? Because in the subset axiom, we have to explicitly say how we define, in this case, the graph of G, how we explicitly find these elements. We need to be explicit, have a formula, and first of the formula that defines the set so that we can have the set. Now here, we are not having an explicit formula. We're just saying choose an element. And choosing an element is fine, but this set B here might be a huge set and not finite, it might be infinite or very, very infinite. And how to choose an element for each element. So we have to do like a lot of choices. So what do we need here? We need a new axiom. And what is this axiom called? As you might guess, is the axiom of choice. The first, we're going to see various different ways of us expressing the axiom of choice. Don't worry, we're going to talk about the axiom of choice quite a bit. This is the first one, and when we need it for this very simple observation about this very simple observation of having a left inverse if and only if you're onto, we need the axiom of choice already. And it says like this, it says the following: for every relation R, there is a function, let's call it G, included in R, so that means a set of pairs, including the set of pairs, with the same domain. Okay, so in pictures, we have a relation, and let's call them backwards because in the previous case, this is the B, this is the A of the previous case. And the relation in the previous case was the inverse, right? So here we wanted G to be a subset of F inverse. Axiom of choice just works for any relation in general. F inverse is a relation, by the way. It might not be a function if F is not one-to-one, but it's still a relation. And all we wanted there is to take a subset of that relation, a sub-function of that relation. So let's do a little picture here. So we have every element here is related to an element here, every element related, and maybe some elements are related to two elements, and this one comes from here. Maybe this one is actually related to another element right here. And what we want is to take a function. This one right there, this relation right there, is not a function. But why is it not a function? Well, because like if you see, this guy goes to two elements, and this one goes to two elements, this one goes to two elements. They are not a function. Each one has to go to one. So now we want to define this function G, and for that we need to map everybody to a single element. So we need to say, okay, this one, well, this is only one option. This is gonna go right here. This guy, well, it's a function. So it can only go to one guy. It could be the same one or not, doesn't matter. We make it go there. And this guy, we make it go there. Okay, so now we have that the red is a function. Each element goes to one. It's a subset of R as a set of pairs, and it's a function. And the domain is the same thing. It's all the same 3 points in the domain, right? So this version of the axiom of choice, in the picture when everything is finite, is trivial. In the finite case, we don't need to call the axiom of choice for this. When it's interesting, it's when you have infinite sets, because when you have infinite set, you have to make infinitely many choices. And making infinitely many choices, well, we'll talk about this later. All right, see you guys next time.